Hey, welcome back. So let's take a look at that second example again. We want to write a double integral that will calculate the area between two circles. Now we're not going to go anything fancy here. For this one, we're going to use the rectangular method. In other words, we're going to keep this in terms of x and y. To do this, I have to determine if I want to do horizontal rectangles or vertical rectangles. I'm going to keep mine vertical. So I will have to take the area of the big circle minus the area of the small circle. And if I go rectangularly, there's my big circle. The top of that big circle is the square root of 9 minus x squared, and the bottom being negative square root of 9 minus x squared. So for the big circle, I know that my change in y's are going to go from negative square root of 9 minus x squared to positive square root of 9 minus x squared, while the change in x's are going to go from negative 3 to 3. For the small circle, I deal with this vertical rectangle. The top being, of course, the square root of 1 minus x squared, and the bottom being negative square root of 1 minus x squared. So for the small circle, my change in y is going to go from negative square root of 1 minus y squared to positive square root of 1 minus y squared. And my changes in x goes from negative 1 to 1. So to get the area, again, I have to do the big one minus the small one, so I actually have to do two integrals. dy dx, negative square root of 9 minus x squared to positive square root of 9 minus x squared, negative 3 to 3, minus, and I'm going to do the smaller one, double integral, dy dx, negative square root of 1 minus y squared to positive 1 minus y squared, or x squared, sorry about that, x, there were x's. There we go. And from negative 1 to 1. And that would give us our area. Now that looks pretty darn complicated to solve. It wasn't hard to set up. It only took us a couple of minutes. But it looks complicated to solve. Now let's convert this into polar form and write a double integral that can be used to calculate the area. And we did this already up here. But we're going to go ahead and revisit that. If I'm looking at my shaded region here, from the center, I have a radial arm connecting it. I need my change in r. Well, my change in r, that's my change in radius, goes from 1 to 3. Only for the shaded region. I'm only interested in the shaded part, so I don't care about anything else. My change in angle, theta, well, we're going to go full circle. That's 0 to 2 pi. So our area, now we do have a special little formula here. It's not just dy dx with dr d theta, it is r dr d theta. Check out the other two videos about where that comes from. R dr d theta, and our double integral, r is first, so it goes from 1 to 3 and 0 to 2 pi. And this looks much easier to solve. Right there. So, remember, and this is the area. This is that base region of the area. So this is our base region that we're looking to find there. Change in r, change in theta. Right there. That's our base region. So how can we write a double integral for the area from example 1? Again, we've already done that. And again, so it's just more of a review for us. So I know that excuse me, that my limits here, my change in radius is going to be from 0. I'm starting here at radius of 0, and I'm moving all the way out here for a radius of 2. So I know that's from 0 to 2. My change in theta, it's measuring up this way, from 0 to pi over 2. So my area, once again, my double integral, r dr d theta, and over here we have from 0 to 2, and then from 0 to 2, with pi over 2, sorry, pi over 2. Let me get rid of that. There we go. All right. Now, so again, if we look at this again in a more generic form, again, let's take a look at this. It's this little rectangle. As delta r goes to 0, if we let delta theta go to 0, these two radial lengths become the same, or this is my arc length. My arc length on bottom and my arc length on top become the same. So I'm going to get these two become S. My change in R, that's just my length, though, and that's a change in R there. Those become the same. So we would get an area of looking at a rectangle of my arc length S times delta R. Well, what is S equal to? Again, it is my R theta dr, delta R there. So what we wind up with is, and theta is getting really small, so we can say area equals R d theta dr. And as R gets really small, or as theta gets really small, we get our change in area equaling R dr d theta. So if we go back up here, let's take a look here. Let's go back up here. If we take a look at this, remember, this is arc length times my change in R. So the R, this R d theta, that's our arc length of an infinitely small little rectangle right here. And there's my radius. So by taking that arc length by the radius, we get the area of this rectangle as theta goes to 0. And that's where our formula comes from. And this is the conversion for us right here. It says in rectangular form, this is a conversion from rectangular to polar. In rectangular form, the change in area of this dA right there, that's on our xy plane. Over here, dr d theta, right here. Well, over here we have our change in theta, and over here we have our change in radius. All right. So let's sketch some regions if possible and solve. Okay, so here we go. We want to sketch the region of R, if possible, solve the double integral. So we're not going to be able to solve these, but we can sketch these. So let's go and take a look here. So for the first one, if I take a look here, remember it's dr d theta right there. So they're telling me that the change in radius is going to go from 0 to pi over 2. And that, oops, sorry, that's the change in theta. The change in radius, let me see if I can get this better, that the change in radius is going to go from 0 to 4, and that the change in theta is going to go from 0 to pi over 2. So I want to draw this. Well, what is this talking about here? Well, that's only a quarter of a circle with radius 4. I'm only going from 0 to pi over 2. That's only a quarter of my way around the circle. So this is a quarter circle of radius 2. So I can draw that. Radius 4. There we go. So from 0 to pi over 2, and I'm looking at a radius of 4. And that's the region we're looking at. And there's the region we are looking at. Well, let's look at the next one. Over here, to get our limits, my change in radius is 4 to 5. I'm going from 4 units to 5 units. My change in theta, going around full circle, 0 to 2 pi. So what this is, well, this is the region between, this is going to be the region between two circles. So if I were to sketch that, one circle is going to have a radius of 4. The other circle is going to have a radius of 5, not drawn to scale. And we're looking for that region in between them. Alright, this is a different one right here. Alright, so let's take a look here. So, let's see here. This one right here says my radius, my change in radius is going to go from 0 to cosine of theta. While my angle, theta, is going to go from 0 to pi. So what are they telling us? That the maximum radius is cosine of theta. In other words, as theta goes from 0 to pi. So what are they asking to do? So we've got the maximum radius is cosine of theta as theta goes from 0 to pi. So what they're asking us to do is just basically sketch the function r equals cosine of theta on 0 to pi. Now you might recall from pre-cal that this is a circle of diameter 1 on the x-axis. So I can draw that. On the x-axis, there's 1. I just draw my circle. There's my radius. Right there. We can solve this one. Let's go and solve this one. If I integrate this with respect to r, we would get r squared over 2 from 0 to cosine of theta, which would equal cosine squared theta over 2. And then we would integrate that with respect to theta, so we would get 1/2 cosine squared theta d theta from 0 to pi. Now this should look a little familiar to you. We saw these in calculus last year. The area of a polar was 1/2 r squared d theta. There it is. All right, so we can't do cosine squared, but we can use our double angle. So 0 to pi, this is 1/2 of, let me see, factor out that 1/2. And cosine squared of theta, if you forgot, cosine squared of theta is equal to 1/2 plus 1/2 cosine 2 theta, right there. And so if we integrate this, so we rewrite this, we get 1/2 plus 1/2 cosine 2 theta d theta, and that I can integrate. We get 1/2, and this is going to become, what's this? 1/2 theta plus, let me see here, this becomes 1/4 sine 2 theta from 0 to pi. And if you plug pi in, we get 1/2. This becomes pi over 2 plus sine of 2 pi is 0, so that just becomes 0, minus, plug in 0, I get 0 minus sine of 0 is just 0, and we get pi over 4. Right. Our next example, let's go see if we can try this one. Looking at the domain, we know that the radius is changing from 0 to 3, and theta is changing from 0 to pi. Now, take a look here. Because I'm multiplying this cosine of theta, this is actually a volume question. We're actually looking for a volume here. Oops, can't spell volume right. This is actually a volume question. So if I were to sketch out that base, though, I'm going from 0 to pi with a radius of 3. So if you notice, this is really just a semicircle on the xy plane. But we are going to project this to the function. To the function f of r theta of cosine of theta. We're going to project that up to this surface here. So now my function in terms of r and theta. So this is on the xy plane here, but we're going to project it up to the cosine graph up there and find that volume. So I can now solve this. If I were to solve this, I'm integrating with respect to r. This just becomes, let's see here, if we were to integrate this with respect to r first, we're going to get r squared over 2 cosine theta from 0 to 3, which is 9/2 cosine theta. And now I'm going to integrate that with respect to theta. So 9/2 cosine theta d theta from 0 to pi, and that just becomes what's that? 9 halves sine theta from 0 to pi, and sine of pi is 0. Sine of 0 is 0. So we get an area of a volume of 0. Okay, interesting problem. All right, I hope you enjoyed the video. I know it's kind of lengthy, but make sure you get those down. And going to the next one, we'll continue on. Bye-bye.